Select the major product of the following reaction. To approach this problem, we need to look at both the starting material and what we are reacting it with in order to decide what sort of reaction this is. Our starting material is an alkene, and we are reacting it with a solution of water and sulfuric acid. Since sulfuric acid is a strong acid that dissociates completely in water, what we are really reacting this alkene with is a solution of hydronium ion in water. This reaction is the acid-catalyzed hydration of an alkene. This reaction involves a carbocation intermediate, and the stability of that carbocation intermediate will guide what constitutional isomer of the product we form. Carbocations are prone to rearrange if they can do so in a way that makes them more stable. In order to make sure we don't miss a rearrangement, we want to draw the mechanism and take a close look at the carbocations that are formed. The alkene will be the nucleophile. The hydronium ion will be the electrophile in this first step. So the alkene will react with that electrophilic hydrogen, and this will break the bond between the hydrogen and the oxygen. In this step, the hydrogen will add to the less substituted carbon atom of the alkene in order to give us the more substituted and thus more stable carbocation. The structure of that initial carbocation is the following. And this is a secondary carbocation. With all carbocations, we want to look and see, can they become more stable? Tertiary carbocations are lower in energy than secondary carbocations. So we want to look to see if we can have a rearrangement that would give us a tertiary carbocation. On this next store carbon atom, we have a methyl group. That methyl group can shift, and this will give us a lower energy, more stable tertiary carbocation. A carbocation is a very strong electrophile and can react with a nucleophile that's in solution. Our solution is hydronium ion, and it should also have in there its conjugate base, which is water. Water is a nucleophile. So the lone pairs of electrons on the oxygen can act as a nucleophile and add to this carbocation. And what this will give us is the following structure. And if we look at this structure and compare it to our options, it appears to be the conjugate acid of B. In the last step of this reaction, we will remove one of these hydrogens to get the neutral alcohol product B. In an aqueous solution, we have plenty of water around, and water can act as a base to do this final proton transfer step to give us the alcohol B as the product.